Hello students, today we are going to discuss about one of the basic principles of polarization of light called Malus law. Malus law can be detected by superimposing two polarized lenses. One such example is presented here. Two Polaroid sunglasses were placed one above another, and it can be seen as you rotate one of the polarized sunglasses relative to the other, the intensity of light passing through these sunglasses changes. Like in the first configuration, the bottom sunglass is oriented along east-west direction, and it can be seen that the word polarization at the back can be fairly visible through these two sunglasses. However, if you rotate one of the sunglasses towards north-south direction, that is by an angle 90 degree, the word polarization is invisible. In this particular configuration, that is configuration 2, the two overlapping sunglasses eliminate all rays, making it impossible to see through. Other combinations are demonstrated in 3 and 4, and it can be seen that the intensity, as you change the orientation or as you rotate one of the sunglasses relative to the other, the intensity of light passing through these two sunglasses changes. And this is what is being demonstrated and formulated by Malus. Till the beginning of 19th century, it was believed that light can be polarized only by passing it through a calcite crystal. In 1808, a French physicist, Etienne Louis Malus, showed that the light can be polarized by reflection. He discovered natural light become polarized when it is reflected by a glass surface. He found that for a light reflected at an angle of incidence 57 degree could be extinguished when viewed through a calcite crystal. So when the light reflected at an angle 57 degree viewed through a calcite crystal, no light seems to reach the eye, or the light can be completely extinguished. However, he was unable to obtain the relationship between polarizing angle and refractive index, and which was later formulated by Brewster. But he proposed that natural light consists of two polarizations which are perpendicular to each other. One is your S polarization, the other one is P polarization. The term S stands for Schenkrest, meaning perpendicular. It's a German word. This is our S polarization. The other one is P polarization, meaning parallel. P stands for parallel, meaning parallel. So he proposed that a natural light consists of two polarizations. One is S polarization, the other one is P polarization. He also observed that the intensity of the reflected light varied from a maximum to a minimum as the crystal is rotated. As you rotate this crystal, the intensity of the reflected light varied from a maximum to a minimum. Malus explained that amplitude of the incident light can be resolved into two components, E naught cos theta and E naught sin theta, along and perpendicular to the plane of transmission of the analyzer. This is the perpendicular component. This is the component parallel to the path axis or the transmission plane of the calcite crystal. He proposed that the amplitude perpendicular component E naught sin theta is blocked, whereas the parallel component of the amplitude E naught cos theta is allowed to pass. Squaring this amplitude relation, the intensity relation, and that is I is I naught cos square theta. This relation is known as Malus law. Malus law could be stated as the intensity of a polarized light transmitted through an analyzer varies as square of the cosine angle between the plane of transmission of the analyzer and the plane of the polarizer. So, Malus law, that is the variation of the intensity of light with the angle of the transmission planes, can only be seen for a polarized light. When you pass an unpolarized light through a polarizer, the intensity of light is reduced to half, and its intensity will not change on rotating the polarizer in a plane perpendicular to the direction of propagation. The reason behind this is the electric vibrations of the unpolarized light can be resolved into two components, S polarization and P polarization. One parallel to the path axis, the other perpendicular to the path. The one parallel to the path axis of the transmission plane is termed as P polarizations. The other perpendicular to the transmission plane is termed as S polarization. And that is true for any orientation of the polarizer in a plane perpendicular to the direction of propagation of the unpolarized light. The light after passing through the polarizer, or the light after getting polarized through the polarizer, when detected through an analyzer, shows the effect proposed by Malus. That is, the light whose intensity was I0 by 2 after passing through this polarizer, which is in this particular case termed as analyzer, having the transmission plane or the path axis at an angle theta relative to the transmission plane of this polarized light, will show a variation proposed by or formulated by Malus. That is, I in this case, or IT in this case, would be I0 by 2 cos square theta. So it should be made very clear that if an unpolarized light is first passed through a polarizer for any orientation of the polarizing of the transmission plane of the polarizer, the intensity will always be reduced to half, roughly. It is only this polarized light after passing through an analyzer will show effect proposed by Malus. So this is Malus law. Let us now test our understanding by solving some of the numericals. So first question is, an unpolarized light of intensity I0 passes successively through two identical linear polarizers A and B, placed such that their polarization axes are at an angle 45 degree with respect to each other or one another. Assuming A and B to be perfect polarizers, that is no absorption losses, the intensity of the transmitted light will be I0 by 4, I0 by 2 root 2, I0 by 2 or I0 by root 2. So if you refer to the previous diagram, so these could be the two polarizers 1 and 2. So let's say name them A and B. An unpolarized light of intensity I0 after passing through first polarizer, its intensity will decrease to half, and then when it passes through another polarizer, that is the analyzer B, the intensity becomes I0, IT becomes I0 by 2 cos square theta, where theta as per question is 45 degrees. Therefore, IT will be I0 by 2 cos square 45 degrees. Cos square 45 degree is 1 by root 2 whole square. So the answer is I0 by 4. The correct option is option A. Let us try another problem. Three polarizers P, Q and R are placed parallel to each other with their planes perpendicular to the axis. Q is placed between P and R. Initially, the polarizing directions of P and Q are parallel, but that of R is perpendicular to them. In this arrangement, when the unpolarized light of intensity I0 is incident on P, the intensity coming out of R is 0. The polarizer Q is now rotated about the z-axis. As a function of the angle of rotation, the intensity of the incident light coming out of R is best represented by, answers are option A, option B, option C and option D. We have to show which waveform would represent the intensity variation of the incident light coming out of R. So as the problem says, it can be seen that the polarizing directions of P and Q are parallel. So the light first unpolarized light passing through polarizer P, whatever may be the polarizing direction, will suffer a decrease in intensity by half. So after passing through polarizer P, the intensity decreases to half, that is I naught by 2. Since Q, polarizing direction of Q is parallel to that of P, so the intensity after passing through Q will remain as I naught by 2. The polarizing direction of R is kept perpendicular to that of P and Q, so after passing through R, the light completely extinguishes because the intensity drops down to 0. That is the initial instant. We could draw the same as follows. So let these be three polarizers, polarizer P, Q and R. An unpolarized light of intensity I naught is passing through these polarizers P, Q and R. Initially, the polarizing direction of P is this, of Q is this, and of R is this, which is perpendicular to P and Q. So in this particular case, we will get a zero intensity here. Now from this intensity, Q is being rotated. Let this be the Z direction, the direction of propagation of light be the Z direction. So about Z direction, Q is being rotated. Let's say at any later instant of time, the new position of the polarizing direction of Q makes an angle theta with its previous direction, that is the polarizing direction of P. The light of intensity I naught after passing through P will suffer a decrease in intensity to I naught by 2. After passing through Q will suffer an intensity decrease as per the relation proposed by Malus, that is I naught by 2 cos square theta. Since this polarizing direction of Q has moved by an angle theta, now the angle of polarizing, the angle between the polarizing direction of Q and R must be 90 minus theta, that is this direction must be 90 degree minus theta. So the light after passing through this polarizer, when the polarizing directions of P and Q and R makes an angle 90 degree minus theta, must have an intensity I naught by 2 cos square theta cos square 90 minus theta. So the final intensity after passing through R must be IT, that is equal to I naught by 2 cos square theta cos square 90 degree minus theta, which can be written as I naught by 2 cos square theta sin square theta. Let us find out the values of theta for which this intensity IT becomes 0. The intensity IT will become 0 when cos theta is 0 or sin theta is 0. Cos theta will be 0 when theta cos theta will be 0 when theta is n plus 1 by 2 phi, where n is a number, where n is an integer, 0, 1, 2 and so on. So for theta equal to pi by 2, 3 pi by 2, 5 pi by 2, the intensity coming out of R, it will also be 0 when sin theta is 0, and sin theta will be 0 when theta is equal to n pi, that is when theta is 0, pi, 2 pi and so on. So looking into the options, we find that the final intensity coming out of R will be 0 when theta is 0, pi by 2, pi, 3 pi by 2, 5 pi by 2. So option A and option D are not correct. Option B and C, the correct answer must be between option B and C. Both the waveforms has a maxima between 0 and pi by 2. So let's say pi by 4. Look the case at an angle pi by 4. At an angle pi by 4, the intensity coming out of R must be I naught by 2 cos square pi by 4 sin square pi by 4. Which is I naught by 2 times 1 by 2 times 1 by 2, that is I naught by 8. So the correct option in this case is option B. So answer is B. So you can try many such problems based on this simple law called Malus law. Only thing you have to ascertain is the light first passing through a polarizer suffers an intensity decrease of half, that is its intensity will decrease by half, and then when it passes through another polarizer it will show the relation formulated by Malus. Thank you.